As we saw in our simulation, there are a variety of factors that can impact the reaction rate. So we know that by increasing our temperature, we're going to have our molecules move faster. Our kinetic energy goes up, and so molecules start to move faster. So what that means for our reactions is that our molecules are going to be, since they're moving faster, they're going to run into each other more, so we're going to increase our number of collisions, which will help us have more reactions, as well as our energy that the molecules are colliding with each other goes up. So we'll have an increase in energy, which will help our reactions happen faster. This helps our molecules get over our activation energy, which is our little energy barrier that they have to go over for a reaction to proceed forward, as well as the orientation of the molecules. So if we have something like A, B reacting with C to form A plus BC, we need C to hit into this side of the molecule. If C hits into A, then this reaction won't happen. So the orientation of the molecules also matters. So let's talk about what in the rate law changes with temperature. So we talked about as we increase our temperature, our rate is increased. So remember, rate equals K times our reactants to their orders, right? And so the orders and reaction concentrations aren't related to the temperature, but what is our rate constant. So K is temperature dependent, and so as the temperature goes up, so increase in temperature means we're going to increase our rate constant. And in general, approximately, the rate constant is going to double with every 10 degrees Celsius increase. So here is a picture of a reaction happening. We have some photoluminescence with a glow stick. So in hot water, it's going to burn brighter, so the reaction is happening a lot faster than in the cold water. Now overall, the same amount of reaction is going to happen, but it's happening a lot slower in the cold water. So here we can see our rate constant versus temperature. So it follows an exponential rise. So as we increase our temperature exponentially, our rate constant is going to increase. And we will talk a little bit more about that relationship soon. So now also we think about the frequency of collisions. So the collision model is based off kinetic molecular theory, which we did in the gas chapter. So molecules are going to hit into each other, and when they collide, they can potentially react. So the more collisions we have, the more reactions are going to happen, and that's going to happen as we either increase our temperature or increase our concentration of our reactants. For a chemical reaction to happen, we're going to have to break reactant bonds and form new bonds from our products. So to do that, we have to hit with enough energy to break those original bonds, right? We have to overcome the bond enthalpy, and then bonds will get formed and release new energy. Orientation is going to matter. So here we go. If we have a reaction where we form chlorine, so Cl2, if I have this molecule that has chlorine and it hits into a chlorine atom directly, then they're going to interact, so that reaction can happen. But if I take the same or a similar molecule and I rotate it, so that way the chlorine atom is facing away and it hits into this molecule, or this atom A here, then our reaction won't happen, and we will just have basically an insufficient collision where the collision doesn't result in a reaction, even if we have enough energy. So in order to break bonds and form new ones, atoms need to be in the proper position or proper orientation. And then the last thing we'll talk about regarding those trends is the activation energy. So this is the minimum amount of energy for a reaction to take place. So we have to overcome this energy barrier For each individual collision, the reactants need to hit each other with enough energy to go over the reaction barrier in order to form their products. Now, it doesn't matter if the products have an energy above or below where the reactants start. It just matters, can they get over the bump? So just like with this golf example. When they are at the top of the bump up here, we say that they are in a transition state. So this is a really high energy state. Because of that, it's really unstable. So they're up there for just a very instantaneous moment, and that's where the atoms in each of the molecules are rearranging, and you have this kind of in-between reactants and products state. And the energy we need to get to our transition state is that activation energy. So those are kind of related. So at the activation energy, we are at our transition state. That's pretty cool actually, because this model for transition state, for this activated complex is another name for it, was developed by Henry Eyring, who is a chemist who taught at the University of Utah, and his work was foundational in getting Nobel Prizes to many other chemists. So pretty cool that that happened basically in our backyards. So what we're gonna do is plot the energy that our reactants have versus the progress of the reactants, where our reactants are written on the left side, our products are written on the right side, and we put our initial energy of our reactants. Now we could calculate that. That's our delta H of our reactants for those molecules. And then I'll have my enthalpies of my products here. Now, we talked about endo versus exothermic will tell us, do my products end above or below my reactants? But now we're going to focus on this part. So the activation energy is the energy it takes to get from your reactants over the bump so you can form your products. So this is our activated complex for this reaction, where I have this molecule here, and initially it is a linear molecule, and what's happening is our carbon and nitrogen is switching places. So I need to break this bond here and then reform a bond with carbon. And so in order to do that, I'm going to have to rotate the carbon and nitrogen around. So the activated form has this in-between phase where they're not connected really, but there's still some kind of attachment. It's very high energy, so it's very unstable. And then once it has enough energy to hit this point up here for the activated complex, then the reaction can easily go down and proceed to the products. So the endothermic and exothermic really just have to do with that initial state and final state. It has nothing to do with the activation energy, but our rate constant is going to depend on our activation energy. So if I have a really high activation energy, then it's going to be harder for molecules to get over the bump. So it's going to be a slower reaction. If I have a smaller activation energy, then that reaction will go faster. So we'll be able to relate those two concepts together. So here I want you to kind of see this trend. We've seen it before many times now. And so remember, this is a plot of the fraction of molecules over energy. And so at any given temperature, our molecules will have a range of kinetic energy. So basically a range of velocities that they are moving at. At lower temperatures, I'm going to have less molecules moving faster, which makes sense, and at higher temperatures, I'll have more molecules. Now we can plot our activation energy here, and so any molecule that is above this energy level will if they collide, they should be able to get over the energy barrier. So this will help us to know, this kind of explains why at a higher energy, we're going to be able to react more, because more molecules can get over that activation energy. And you saw in the simulation that on average, molecules were moving a certain way, but there were some that were slower, some that were faster, and those faster ones were the ones that were able to have a successful reaction. So here we have a few different graphs, so different reactions, they have different energies. And we want to rank the forward rate constants from smallest to largest, assuming they have the same value for frequency factor, which we'll talk about soon. So what we want to do is think about who's going to move faster. So for my forward direction, I'm going to rank, I have an activation energy of 15 kilojoules per mole here, 25 here, and 20 here. So fast means a low bump. So who has the lowest bump? Reaction 1 has the smallest activation energy. So if I rank it from activation energy, I'm going to have the lowest will be reaction 1, and then reaction 3, and then reaction 2 has the largest. So if I want to rank it as far as speed, which is how we can rank the rate constant, so large rate constant equals fast. So who's going to be going the fastest is going to be the one that has the lowest activation energy, so it'll be opposite. So it'll be 1, oops, this should be a 2. 1 will be the fastest, and then 3 will be the next one, and then 2 will be the slowest because it has the biggest energy bump. Okay, now I want to do the same thing, but for the reverse reaction. So now we want to think about how much energy does it take to go from this way over to here. So if I look at this one, this one's going to take 10 joules per mole and 15, so a total of 25 to go up this way. This number 2 is going to take 15 plus 25, so 40 to go that way. And then here, this whole thing equals 20. This small amount is 5, so then the activation energy to go up there will be 15. Okay, so if I want to go the rate constants from slowest to fastest, so slowest is going to have the biggest barrier, so it's going to be 2. And then the next one will be, the next largest one is number 1, and then the fastest one in the reverse direction will be 3. So that is how we could rate the rate constants from slowest to fastest, and if I wanted to do activation energies, it would be the opposite order. So to finish us off here, we're going to note the mathematical relationship between activation energy, temperature, and I want to even say the rate constant K. So we saw before that as I had my temperature increase, my rate constant went up exponentially. So if I want to know that relationship, it is given by the Arrhenius relationship, which says that the rate constant K equals a constant, times by E exponential to the negative activation energy over RT. Since we're dealing with energy, the R constant here is going to be 8.314 joules per mole Kelvin. So we need to make sure that our temperature is in Kelvin and that our activation energy is in joules for that to all work out. Now the A here is our frequency factor, so that helps us to know, how well the reaction will occur, how easily it will occur. Now I don't know about you, but exponential relationships are kind of hard to interpret. So what scientists have done is we tried to take this exponential curve and make it into something that looks like a straight line, which is what we've been doing in the other sections as well. We saw that before with the Clausius-Clapeyron equation and vapor pressure, where that was exponentially related, and we took the natural log, plotted versus 1 over temperature to give us the slope, right, which was gave us some value. So now we're going to do that again. So we want to get rid of that exponential. So what we're going to do, and I'm going to do it I'm going to show my work first, and then I'll give you the end result. So feel free to just kind of watch. So if I have K equals A e to the negative activation energy over RT, what I want to do is take the natural log. That will be the opposite of my exponential. So I'm going to do the natural log of both sides here. So I get natural log of the rate constant k equals, now if I have two things that are being multiplied here, when I do a natural log, what we can do is add them. So I'm going to do natural log of a plus the natural log of e to the negative a activation energy over RT. Now this whole thing, this natural log of e, cancels out, so I can actually bring this whole thing down. So what I get is natural log of k equals negative EA over RT plus natural log of a. So I just moved that over. So this means that if we plot, again, a natural log of k over 1 over t, then my slope will give me some interesting info. So I'm going to pull this out and write it in a certain way that will hopefully help us with graphing. So the big takeaway for you is natural log of our rate constant equals negative activation energy over R times 1 over t plus the natural log of a. Now this should look really similar to a line, okay, where here is y, here is x, and what I end up getting is y equals mx plus b. So if I plotted natural log of k over 1 over temperature, or versus 1 over temperature, then my slope will equal negative activation energy over R, so that's how we calculate activation energies. And my intercept, so B, is equal to natural log of A. So if I want to find A, I can just exponential the whole thing and get that value. And if I want to find activation energy, I just multiply my slope by negative R. So we're going to practice that. If you only have 2 points in your curve, what you can do also is do the natural log of K1 over K2, if we have only 2 data points, equals the activation energy divided by R times 1 over T2 minus 1 over T1. Again, make sure you're in Kelvin, make sure your activation energy is in joules, and remember, 1 goes up first front here, and then in the back here. Here we go. We have a table, shows the rate constants for rearranging methyl isonitrile at various temps. So we want to calculate the activation energy. And then we'll find the rate constant at 430 and then find the value of A. So you're going to need to open your Google Sheets or Excel or something like that so you can graph this. So if I want to plot, to make this exponential curve, I want to plot, my x needs to be 1 over t and my y needs to be ln of k. Okay, so that'll be x and y. So I'm going to need 2 new plots here, one that's 1 over temperature and one that is the natural log of k. So let me plug that into my Google Sheets and get those values. So first thing you actually need to do is get your temperature in Kelvin. So temperature in Kelvin, so we're going to do equals this cell plus 273. And then what I'll do here is I'll do equals 1 over this cell to give me the 1 over temperature, and for this one I'll do equals natural log ln parentheses of this cell to give me this value. So let me get those for you. My temperatures in Kelvin are, first off, this one here is 462.7, 471.9, 503.9, and 524.2. Then when I do 1 over those temperatures, I get 0.00216, 0.00212, 0.00199, and 0.00191. For my natural logs of k, I get negative 10.589, negative 9.855, negative 7.3697, and then negative 5.757. Now, in my actual sheets, I will have all of the values, not just these rounded numbers, when I plot. So then I'm going to highlight the cells that have a 1 over temperature and ln of k. That should be my x, this should be my y, and I'll get a graph. So let's see what that looks like. So I get a graph that looks like, so ln of k and a 1 over temperature here. It looks like that. So negative slope. I have my equation. So it has the y ln of k equals, my slope for this is negative 19.038 times x. Now my x is 1 over t. And then plus my intercept b, which is 30.517. So now what I can do is find my activation energy. So remember, the slope equals negative activation energy over r. So I'm going to take my slope, negative 19.038 equals negative EA, which I'm finding, over R, 8.314 joules per mole Kelvin. Now I'm going to multiply by negative 8.314 to both sides to get my activation energy value equal to 158,282. And that will be in joules per mole. So if I want to get that in kilojoules, I'll divide by 1,000. I get 158.3 kilojoules per mole. So pretty high activation energy. I can now find the rate constant at 430 Kelvin by plugging in here if I want to. So I could do natural log of k, which is what I'm finding, equals negative 19.038 times by 1 over 430 Kelvin plus my intercept 30.517. Now I can solve for k. So I'm going to plug in these values real quick. And I find out natural log of k equals negative 13.76. And so to get k by itself, I'm going to do exponential of that. And what I get is that my value for k, so that'll cancel out, equals 1.0560 basically times 10 to the negative 6. And the units are inverse seconds. Now if we look at this, negative or 430 Kelvin is less than the temperature we had to start out with, and so it makes sense that my value is lower than this. So that's good. The last thing is, what's the value of frequency factor A? Well, that will be, we'll find, remember the intercept B equals natural log of A. So my intercept was 30.517 equals natural log of A. So if I take the exponential of that, then A equals 1.7, and it just wants into 1/6, so I'll say 2 times 10 to the 13. So very big number. So long process, but a lot of it's just setting up your curve, and then after that it should be not too big of a deal once you have your linear regression.